Yes, the concerns are legitimate. The grounding practice described poses several risks. Firstly, neutral to ground fault currents. If a neutral wire becomes disconnected or loose, neutral to ground fault currents can flow through the parallel neutral network and return to the source. This could overload the grounding system and trip circuit breakers. Secondly, arc flash hazard. If a fault occurs on one of the transformers, the parallel neutral network could provide a low impedance path for high magnitude arc flash currents to spread throughout the motor control center. Thirdly, overheating and insulation degradation. The high current flow through the parallel neutral network could overheat the wires and insulation, leading to insulation failure and potential fire hazards. The grounding practice described violates several code requirements. NEC 250.26 states that neutrals must be connected to the grounded circuit conductor at only one point. NEC 250.26c specifies that neutral conductors must not be used as equipment grounding conductors. NEC 250.24b2 requires that equipment grounding conductors must be routed with the circuit conductors. To mitigate the risks and address the code violations, the following actions are recommended. Firstly, remove all parallel neutral connections. Secondly, connect each control transformer's neutral only to the grounding point at the source. Thirdly, ensure that the equipment grounding conductors are properly routed with the circuit conductors back to the source. Fourthly, verify that all neutral conductors are adequately sized and protected. Fifthly, consider implementing a neutral monitoring system to detect an alarm on any neutral to ground faults. Control transformers are essential components in various electrical systems, providing a means to step down voltage levels to supply power to control circuits and other low voltage devices. However, improper grounding practices associated with these transformers can introduce several safety hazards and operational issues. Understanding the risks and adhering to relevant codes and standards are crucial for ensuring a safe and reliable electrical installation. One of the primary concerns with control transformers is the potential for ground faults. A ground fault occurs when an unintended electrical path develops between a live conductor and ground. This can happen due to insulation failure, damaged wiring, or other factors. In the context of control transformers, a ground fault can lead to several consequences, including the risk of electric shock, equipment damage, and fire. To mitigate the risk of ground faults, it is essential to implement proper grounding techniques. Grounding involves connecting the electrical system to the earth, providing a low impedance path for fault currents to flow back to the source. This helps to quickly trip circuit breakers or ground fault circuit interrupters, interrupting the flow of current and preventing further damage or injury. Several code requirements address the proper grounding of control transformers. The National Electrical Code (NEC) provides comprehensive guidelines for electrical installations, including grounding and bonding requirements. Some key NEC sections relevant to control transformers include Article 450, which covers transformers in general, and Article 250, which addresses grounding and bonding. One important requirement is that the secondary side of a control transformer must be grounded if the voltage to ground exceeds 150 volts. This means that if the secondary voltage of the transformer is greater than 150 volts, the neutral point of the secondary winding must be connected to ground. This grounding connection helps to limit the voltage to ground during a fault condition, reducing the risk of electric shock. Another critical aspect of grounding is the use of equipment grounding conductors. Equipment grounding conductors are used to connect the non-current carrying metal parts of electrical equipment, such as transformer enclosures, to ground. This provides a low impedance path for fault currents to flow back to the source, helping to quickly trip circuit breakers and prevent equipment damage. The equipment grounding conductor must be properly sized and installed to ensure effective grounding. In addition to grounding, bonding is another essential safety practice. Bonding involves connecting all metal parts of an electrical system together to create a continuous electrical path. This helps to minimize voltage differences between different parts of the system, reducing the risk of electric shock. Bonding is particularly important in areas where there is a high risk of moisture or corrosion. In the context of control transformers, bonding involves connecting the metal enclosure of the transformer to the equipment grounding conductor. This ensures that the enclosure is at the same electrical potential as ground, reducing the risk of electric shock if someone comes into contact with the enclosure. Another important consideration is the use of ground fault protection. Ground fault protection devices, such as ground fault circuit interrupters, are designed to detect ground faults and quickly interrupt the flow of current. These devices are particularly useful in areas where there is a high risk of electric shock, such as wet locations or construction sites. Ground fault protection can be implemented at the transformer itself or at the panel board that supplies power to the transformer. In addition to these safety measures, it is also important to follow proper installation practices. Control transformers should be installed in accordance with the manufacturer's instructions and all applicable codes and standards. This includes ensuring that the transformer is properly mounted, that all wiring connections are secure, and that the transformer is adequately ventilated. Regular maintenance is also essential for ensuring the safe and reliable operation of control transformers. This includes inspecting the transformer for any signs of damage, such as cracks or corrosion, and testing the insulation resistance of the transformer windings. Any damaged or defective components should be replaced immediately. Proper grounding and bonding are essential for ensuring the safe and reliable operation of control transformers. By following the code requirements and implementing appropriate safety measures, it is possible to minimize the risk of ground faults, electric shock, and other hazards. It is also important to provide adequate training to personnel who work with control transformers. This training should cover the principles of grounding and bonding, the relevant code requirements, and the proper procedures for installing, maintaining, and troubleshooting control transformers. Understanding the NEC requirements for control power transformers is essential for ensuring electrical safety and code compliance. These transformers, typically used to supply power to control circuits and other low-voltage devices, must be installed and maintained according to specific guidelines to minimize the risk of electrical hazards. Article 450 of the NEC covers the general requirements for transformers, while other sections address specific aspects such as grounding, overcurrent protection, and wiring methods. One of the key NEC requirements for control power transformers is proper grounding. According to NEC 250, transformers must be grounded to provide a low impedance path for fault currents and to limit voltage to ground. The grounding method depends on the transformer's voltage and configuration. For transformers with a secondary voltage of 150 volts or less to ground, the secondary neutral point must be grounded. This grounding connection helps to stabilize the voltage and prevent overvoltages during fault conditions. It also provides a path for fault currents to flow back to the source, allowing overcurrent protection devices to quickly trip and clear the fault. The grounding conductor must be sized according to NEC 250.66, which specifies the minimum size based on the size of the transformer's secondary conductors. It is also important to ensure that the grounding conductor is properly connected to the transformer's grounding terminal and to the building's grounding electrode system. For transformers with a secondary voltage greater than 150 volts to ground, the grounding requirements are more stringent. In these cases, the secondary neutral point must be grounded, and the transformer enclosure must also be grounded. This provides additional protection against electric shock and helps to minimize the risk of arc flash. The grounding conductor for the transformer enclosure must be sized according to NEC 250.122, which specifies the minimum size based on the rating of the transformer's overcurrent protection device. In addition to grounding, overcurrent protection is another critical NEC requirement for control power transformers. Overcurrent protection devices, such as fuses or circuit breakers, are used to protect the transformer from overload and short-circuit conditions. The size of the overcurrent protection device must be carefully selected to prevent nuisance tripping while still providing adequate protection for the transformer. NEC 450.3 provides detailed requirements for overcurrent protection of transformers. For transformers rated 600 volts or less, the overcurrent protection device must be rated at not more than 125% of the transformer's rated primary current. This allows the transformer to handle short-term overloads without tripping the overcurrent protection device. However, for transformers with a primary current of 9 amps or more, the overcurrent protection device must be rated at not more than 125% of the transformer's rated primary current. This provides more sensitive protection against overloads and short circuits. It is also important to consider the transformer's inrush current when selecting the overcurrent protection device. Transformers can draw a large inrush current when they are initially energized, which can cause the overcurrent protection device to trip. To prevent nuisance tripping, it may be necessary to use a time delay fuse or a circuit breaker with an adjustable trip curve. Another important NEC requirement for control power transformers is proper wiring methods. The wiring methods used to connect the transformer to the power source and a load must comply with the requirements of NEC Chapter 3. The conductors must be properly sized for the load, and they must be protected from physical damage. The conductors must also be insulated to prevent short circuits and ground faults. The NEC specifies different wiring methods for different applications. For example, conductors installed in conduit must be sized according to NEC 310.16, which takes into account the ambient temperature and the number of conductors in the conduit. Conductors installed in cable trays must be sized according to NEC 392, which takes into account the cable tray's fill capacity and the ambient temperature. In addition to these general requirements, there are also specific NEC requirements for control power transformers installed in hazardous locations. Hazardous locations are areas where there is a risk of fire or explosion due to the presence of flammable gases, vapors, or dust. Transformers installed in hazardous locations must be listed and labeled for use in those locations. They must also be installed in accordance with the requirements of NEC Article 500. Article 500 specifies different protection techniques for different types of hazardous locations. For example, transformers installed in Class I, Division 1 locations must be explosion-proof. Explosion-proof transformers are designed to contain any internal explosions and prevent them from igniting the surrounding atmosphere. Transformers installed in Class I, Division 2 locations must be either explosion-proof or intrinsically safe. Intrinsically safe transformers are designed to limit the amount of energy that can be released into the hazardous atmosphere, preventing ignition. Understanding and complying with the NEC requirements for control power transformers is essential for ensuring electrical safety and code compliance. Proper grounding, overcurrent protection, and wiring methods are critical for minimizing the risk of electrical hazards. It is also important to consider the specific requirements for transformers installed in hazardous locations. By following these guidelines, it is possible to ensure that control power transformers are installed and maintained safely and reliably. The installation of control transformers requires adherence to several National Electrical Code (NEC) guidelines to ensure safety and prevent electrical hazards. These guidelines cover various aspects, including grounding, overcurrent protection, wiring methods, and location requirements. Grounding is a critical aspect of control transformer installation. NEC Article 250 provides comprehensive requirements for grounding and bonding. The primary purpose of grounding is to provide a low impedance path for fault currents, which helps to protect equipment and personnel from electrical shock. Control transformers must be grounded in accordance with NEC 250.20, which specifies the conditions under which grounding is required. Generally, control transformers with a secondary voltage of 50 volts or more must be grounded. The grounding conductor must be sized according to NEC 250.66, which is based on the size of the ungrounded conductors. The grounding electrode system must comply with NEC 250.50, which requires the use of a grounding electrode conductor connected to a suitable grounding electrode, such as a metal water pipe or a ground rod. Overcurrent protection is another essential safety measure for control transformers. NEC Article 450 provides requirements for overcurrent protection of transformers. The overcurrent protection device, typically a fuse or circuit breaker, must be sized to protect the transformer from overloads and short circuits. NEC 450.3b specifies the maximum overcurrent protection for transformers rated 600 volts or less. The overcurrent protection device must be set at no more than 125% of the transformer's rated primary current. For example, if a transformer has a rated primary current of 10 amps, the overcurrent protection device must be set at no more than 12.5 amps. Wiring methods for control transformers must comply with NEC Chapter 3, which covers wiring methods and materials. The wiring must be suitable for the voltage and current levels of the transformer. Conductors must be sized according to NEC 310.15, which takes into account the ampacity of the conductor, the ambient temperature, and the number of conductors in a raceway or cable. Wiring must be protected from physical damage, and conductors must be insulated to prevent short circuits and ground faults. The location of control transformers must also comply with NEC requirements. NEC 450.11 specifies the requirements for transformer location. Transformers must be accessible for inspection and maintenance. They must be located in a dry, well-ventilated area. Transformers must not be located in hazardous locations, such as areas where flammable materials are stored, unless they are specifically designed and listed for use in such locations. Control transformers installed in damp or wet locations must be protected from moisture. This can be achieved by using a NEMA 3R or NEMA 4 enclosure. Transformers installed outdoors must be protected from the elements. This can be achieved by using a NEMA 3R or NEMA 4 enclosure. Control transformers must be installed in accordance with the manufacturer's instructions. The manufacturer's instructions provide specific details about the transformer's installation, operation, and maintenance. The instructions must be followed carefully to ensure the transformer's safe and reliable operation. Regular inspection and maintenance are essential for control transformers. Transformers must be inspected regularly for signs of damage or deterioration. Wiring connections must be checked for tightness. Overcurrent protection devices must be tested to ensure they are functioning properly. Any damaged or deteriorated components must be replaced promptly. Control transformers must be protected from physical damage. Transformers must be located in an area where they are not likely to be struck by moving equipment or falling objects. If transformers are located in an area where they are subject to physical damage, they must be protected by a barrier or enclosure. Control transformers must be properly labeled. The label must identify the transformer's voltage, current, and power ratings. The label must also indicate the transformer's grounding requirements. The label must be permanently affixed to the transformer. Control transformers must be installed by qualified personnel. Only qualified electricians or technicians should install control transformers. Qualified personnel have the knowledge and experience to install transformers safely and correctly. They are also familiar with the NEC requirements for transformer installation. Following these NEC guidelines is essential for ensuring the safe and reliable operation of control transformers. Proper grounding, overcurrent protection, wiring methods, and location requirements are critical for preventing electrical hazards and protecting equipment and personnel. Regular inspection and maintenance are also essential for ensuring the transformer's continued safe and reliable operation. It's crucial to ensure proper grounding and bonding techniques when dealing with control transformers to protect against electrical hazards and ensure safe operation. These techniques involve creating a low impedance path for fault currents to flow back to the source, minimizing the risk of electric shock and equipment damage. Grounding involves connecting the neutral point of the control transformer's secondary winding to the earth. This connection provides a reference point for voltage and helps to stabilize the system. It also provides a path for fault currents to flow back to the source, allowing overcurrent protection devices to quickly trip and clear the fault. Bonding involves connecting all metal parts of the electrical system together, including the transformer enclosure, conduit, and other metallic components. This creates a continuous electrical path that helps to minimize voltage differences between different parts of the system. Bonding is particularly important in areas where there is a high risk of moisture or corrosion. Grounding and bonding should be performed in accordance with the National Electrical Code (NEC) and other applicable standards. The NEC provides detailed requirements for grounding and bonding electrical systems, including control transformers. Proper grounding and bonding techniques can help to prevent electrical shock, equipment damage, and fire. They can also improve the reliability and performance of the electrical system. Here are some specific grounding and bonding techniques to consider for control transformers. Ground the neutral point of the secondary winding. This is typically done by connecting the neutral point to a grounding electrode, such as a ground rod or a metal water pipe. Bond all metal parts of the electrical system together. This includes the transformer enclosure, conduit, and other metallic components. Use proper grounding and bonding conductors. The size of the grounding and bonding conductors should be based on the size of the overcurrent protection device. Install ground fault protection devices. Ground fault protection devices, such as ground fault circuit interrupters (GFCIs), can help to protect against electrical shock by detecting small ground faults and quickly interrupting the flow of current. Inspect grounding and bonding connections regularly. Grounding and bonding connections can loosen or corrode over time, which can reduce their effectiveness. Regular inspections can help to identify and correct any problems before they become a safety hazard. Control transformers are a critical component in many industrial and commercial electrical systems, providing a reliable source of low voltage power for control circuits and other devices. However, improper grounding and bonding techniques can create serious safety hazards. By following proper grounding and bonding techniques, you can help to protect against electrical shock, equipment damage, and fire. You can also improve the reliability and performance of your electrical system. Always consult with a qualified electrician or electrical engineer to ensure that grounding and bonding techniques are properly implemented. Understanding and implementing proper grounding and bonding techniques is crucial for ensuring the safe and reliable operation of electrical systems, including those that utilize control transformers. These practices play a vital role in minimizing the risk of electrical shock, equipment damage, and fire, while also enhancing the overall performance and longevity of the system. Grounding, in essence, involves creating a low impedance path for fault currents to flow back to the source, allowing overcurrent protection devices to quickly trip and clear the fault. This low impedance path is achieved by connecting the neutral point of the control transformer secondary winding to the earth, typically through a grounding electrode such as a ground rod or a metal water pipe. By providing this direct connection to the earth, the system voltage is stabilized, and the risk of overvoltages during fault conditions is significantly reduced. Bonding, on the other hand, focuses on connecting all metal parts of the electrical system together, including the transformer enclosure, conduit, and other metallic components. This interconnected network of metal parts creates a continuous electrical path that minimizes voltage differences between different parts of the system, further reducing the risk of electrical shock. Bonding is particularly important in environments where moisture or corrosion is prevalent, as these conditions can exacerbate the risk of electrical hazards. To ensure the effectiveness of grounding and bonding techniques, it is essential to adhere to the guidelines and requirements outlined in the National Electrical Code (NEC) and other applicable standards. These codes provide detailed specifications for conductor sizing, grounding electrode systems, and bonding methods, ensuring that the electrical system is properly grounded and bonded to minimize the risk of electrical hazards. In addition to adhering to code requirements, there are several best practices that can further enhance the safety and reliability of electrical systems utilizing control transformers. Firstly, it is crucial to use proper grounding and bonding conductors that are appropriately sized for the overcurrent protection device. The size of the grounding and bonding conductors should be determined based on the size of the overcurrent protection device, ensuring that they can effectively carry fault currents back to the source. Secondly, consider installing ground fault protection devices, such as ground fault circuit interrupters (GFCIs), to provide an additional layer of protection against electrical shock. GFCIs are designed to detect small ground faults and quickly interrupt the flow of current, preventing potentially lethal electrical shocks. Thirdly, regular inspections of grounding and bonding connections are essential to ensure their continued effectiveness. Over time, grounding and bonding connections can loosen or corrode, reducing their ability to carry fault currents. Regular inspections can help identify and correct any problems before they become a safety hazard. Finally, it is important to consult with a qualified electrician or electrical engineer to ensure that grounding and bonding techniques are properly implemented. These professionals have the knowledge and expertise to assess the specific requirements of the electrical system and design a grounding and bonding system that meets those needs. By following these guidelines and best practices, you can significantly reduce the risk of electrical hazards associated with control transformers and ensure the safe and reliable operation of your electrical system. Understanding the principles of operation and the safety requirements for these devices is paramount for anyone working with electrical systems.